Hi, in this video we are going to go through some worked examples, finding determinants using the fundamental properties of the determinant rather than using formulas or more direct methods to compute a determinant. Let's begin with the matrix shown here. Can we find its determinant? I recommend that you pause your video, try to solve the problem on your own, and then resume to look at the worked solution. The key thing to recognize about this matrix is that it is a lower triangular matrix. We have diagonal elements, and everything above the diagonal are all zeros. Triangular matrices, whether lower triangular or upper triangular, as well as diagonal matrices, which are special forms of both of these, have a determinant that is given simply by the product of the diagonal elements. So starting with a lower triangular matrix, the determinant of L is simply 2 times -1 times 4 times -3, which is 24, positive 24. Okay. Let's take another example. We find the determinant of this matrix P. Once again, I recommend you pause your video, work through the solution on your own, and then resume to look at the worked solution. Okay. The key feature of P is that it is a permutation matrix. This means that it can be reconfigured into the identity matrix only using row exchanges. That means its determinant has to be plus or minus 1, and the sign of that determinant will depend on how many row exchanges we need to get to the identity matrix. So we can simply walk through this and ask how many times do we need to swap rows. The first step, let's see, we want to get this entry up to the top, so we swap rows 1 and 4. That puts our first pivot where it's supposed to be. We then look, where is our second pivot? Our second pivot is now down on the bottom row. And so now let's exchange the second and fourth row to put our second pivot in position. Then we see, oh, now our third pivot is down in the bottom row, and so we exchange one more time to put our third pivot there. It took us 1, 2, 3 row exchanges to get us back to the identity matrix. When we need an odd number, we take the negative. So the determinant of P is -1. Okay. Now, let's take a matrix of less of a simple form. We find the determinant of this matrix A. Once again, pause your video, try to find it on your own, and then move forward to look at the worked solution. Our matrix A is not in triangular form, so we can't simply take a product of diagonal entries. It's not simply a rearrangement of a triangular form, and so we can't simply do row exchanges. We begin this problem by going through elimination. And we take the same process we always have. Start with our first pivot, eliminate downwards. We already have zeros in the bottom 2 rows, so we just subtract the first row from the second. This gives us 1 minus 1 is 0, 0 minus 2 is -2, 0 minus 1 is -1, and 0 minus 0 is 0. Move down and to the right, another pivot and another elimination step. Again, the bottom row already has a 0 here. We add half of the first row to the third. 1 minus 1 is 0. 0 minus a half is negative a half. And 3 plus 0 is 3. Move down and to the right to our next pivot. One more elimination step. Add 4 times the third row to the last. 2 minus 2 is 0. And 4 plus 12 is 16. We now have an upper triangular matrix. We have done elimination without any row exchanges. Elimination without row exchanges results in an equality between the determinant of A and the determinant of U. So we simply multiply the entries on the diagonal of U. 1 times negative 2 times negative half times 16 gives us positive 16 for our final determinant. Let's do one more example. Find the determinant of this matrix. Once again, I recommend that you pause your video, work through the solution on your own, and then resume to compare with my solution. Once again, we have a matrix that doesn't have any special form, so we begin by carrying out elimination. Eliminate downwards. For the first row, subtract the first row from the second, gives us 1 minus 1, 0, 0, 0, and 1. Subtract the first row from the third, gives us 0. 3 minus 1 is 2. 2 minus 1 is 1, and 1 minus 1 is 0. Subtract twice the first row from the last. 2 minus 2 is 0. 1 minus 2 is negative 1. 2 minus 2 is 0. And 3 minus 1 is, 3 minus 2 is plus 1. We then move over and to the right, but we have a 0 in the position we would like our pivot and non-zeros below. We have to correct this with a row exchange. Let's start counting. 1 row exchange. We do not need to go back after row exchanges like we do in LU decomposition. We just need to count them and carry through with forward elimination. We now have a pivot we can work with. Eliminate the entry below by adding half of the first row to the, or half of the second row to the fourth. Sorry, there should be a 1 here and a 1 here. Negative 1 plus 1 is 0. 0 plus a half is a half. 1 plus 0 is 1. So we would move over and to the right. Again, we have a 0 where our pivot should be, and a non-zero entry below. So we need to do another row exchange, our second row exchange here. And that row exchange gives us now an upper triangular form. When we have elimination that includes row exchanges, we know that the determinant of A has to equal plus or minus the determinant of U. So again, we begin by evaluating the determinant of U. It's a product of the diagonal entries. 1 times 2 times half times 1 is 1. But then we count the row exchanges and adjust the sign as necessary. In this case, we used 2 row exchanges. 2 is an even number, so the sign remains unchanged. The determinant of A is the determinant of U is 1. All right. We've now gone through 4 examples of using the properties of the determinant and how row exchanges are related to that to give us the determinant of a number of different types of matrices. In an accompanying worked example video, we will look at finding determinants using alternative methods, more direct methods, as well as problems of how we use a determinant in different sorts of circumstances. Thank you, and goodbye.